Hello everyone, this is Tim Bergsma at Veteran Research Group, coming back to you for part 2 of the chapter 3 lessons for MI205. Today we just have one topic to discuss, and then we will spend the remaining time with practical exercises, looking at homework problems, answering your questions, etc. And we'll start right in with the concept of scope of function variables. In the book, I give an example that I'm going to reproduce right here. I'll give myself some space on the screen, and we write a short function that will help us illustrate the concept of variable scope. And that should do it. Okay, a quick definition, or at least an informal one. Variable scope refers simply to where a variable can be seen, or the visibility of a variable. As a very general rule, variables defined or modified inside functions are visible only there. But global variables can be visible everywhere. So, to illustrate, let's go ahead and source this function and give it a quick run. We just say, okay, we're going to do something to whatever, 5. Put the parentheses a little closer. And as always, if you're having trouble seeing that or want some clarification, I'm monitoring my question box. You can go ahead and send me a question. So you learned last week, if you didn't know it already, that the return value of a function is the last expression executed. In this case, that is to print a character vector of length 1, the word done. So what happened to x? Well, let's look in our global environment, that's where we work on the command line, and see what is x. X is nothing, x is undefined, and we say, hey, wait a second, here's a definition of x, or at least we passed in the variable and things happened to it. What happened to all those changes? Well, the answer is they stayed inside the function body. When the function was complete, that function environment disappeared and took all the information with it. So if you do something to a variable inside a function, and that operation is important to you, you need to return it. You need to make sure that somehow you send that back out of the function. Actually, you could print something directly to the screen manually, or you could write something to a file, or use the conventional mechanism of a return value to get your information back out. But otherwise, when you pass x to the function do, or something analogous for some other function, you're really operating on a copy of that value and not on the value itself. And that copy stays with the function environment and disappears when the function exits. So what about this function? And it's also from the book, so you can explore it in detail later, see the discussion there. This function takes no arguments at all. We're modifying their definition of do, and we're returning y times 2. Rather simplistic, but it makes a point. Let's source that function. And what we're implicitly saying here, or explicitly saying, is that this function doubles the value of y. Great. Well, let's set y to 3. Well, actually, let's do things just a little differently from in the book. Let's just call the function with no args. That's the way it was defined. And of course, we get an error, as expected, because y does not exist. Now, this part is interesting. We're defining y here, or at least setting it to a value, and we're doing that in the global environment. We could have also done that in the function body up here and done the same thing, and then we'd have a function that really always returns the same value, not particularly useful. But I'm not going to do that for now. I'm just defining y in the global environment, and then we're going to call the function do again, and this time we get a value. So let's try to think about this from R's perspective. R says, okay, I've got to call this function. Do has no arguments. I'm supposed to return y times 2. Well, what's y? I look around. It's not an argument. It's not defined in my function body. So at that point, R will go and look outside of the function body, and it'll look in the global environment and discover a y there. Say, oh, here's a y, fine, I'll use that, and return the appropriate value. There's actually a fairly short and explicit set of rules for where R looks for things that it doesn't find immediately. I'm not going to go into those rules now, but you should be aware of this behavior because it can lead to some surprising and undesired results, or occasionally you can use this behavior much to your advantage. You may see cases of that later in this book. The most important thing to be aware of is that you've got to return your values if you intend to use them later. And also be a little cautious of relying on globally defined values inside your functions. A very good general rule is that anything a function needs to do its job ought to be passed to it as an explicitly named argument. With that, we end the formal lecture portion for this chapter, and we have the whole rest of this hour to answer your questions. Now, there were quite a few exercises specified in the chapter. We looked at some of them in class on Tuesday, and I don't think we worked through any of them. There are others that were at the end of the chapter, which you could have added on your own and worked on during the week. To make best use of your time, I'm going to start simply by working through the problems that you ask me to work through. So we'll skip the ones that you consider trivial, and we'll go right to the ones that you find interesting and work through those. At the end of class, I will post a script that illustrates solutions for every problem in Chapter 3. But right now, we'll take your questions, and if there aren't any, or if we finish all the material very quickly, then we won't waste any more time. We'll just go on to other things. And let me be explicit. When I say go on to other things, I mean if you're done and satisfied, you can leave. And when everyone has logged out of the class, I will leave too. But I'm happy to stay here until 2 o'clock and answer your questions about homework problems or anything else related to R or this course. So you can type something in the question box and say, hey, what about section whatever, exercise 2 or something like that, if that's what you're stuck with or struggling with. If no one has anything that they're struggling with, I might just try 1 or 2 that I found interesting. And we have a question that says, can we go over 3.4.1 exercises? We certainly can. Happy to do that for you. I'll make a little space on the screen here with some return characters. In section 3.4.1, exercise number 1 says, write a function that concatenates a protocol number and a subject ID separated by a hyphen. Okay, this is a little bit of finesse, probably best done with the paste function. And just to remind ourselves how paste works, you can say paste to things like hello, oops, and world. When you do that, R just sticks a space between them, but actually that space is user specifiable. I mean, not the space particularly, but what R uses as a separator is user specifiable. And here we want to specify that the separator be a hyphen. So I'm building this up piecewise using simple things for starters. I'm going to say sep equals hyphen. This time we get hello world with a hyphen. And something disappeared on me here. I'll try to make my window back like yours probably looks. There's hello world with a hyphen. Now we say, great, we have mastered the use of paste command. We're going to use it to write a function. First, we need a informative name for our function. Protocol number and subject. I don't know, we could call it subject ID, because that's essentially what we're trying to create. And we'll say it's a function. We'll say it's a function of protocol number and subject. Pretty obvious. And at this point, I can't think of any good defaults for either of those, so we're not going to provide any. We will force the user to specify protocol and subject, and we'll assume that those are character. So within our function, we'll say ID set to paste, and then we'll use the tricks above, but now instead of hard coding values, we'll use the variables that were passed to us. Paste protocol to subject, and let the separator be a hyphen. If we really wanted to get fancy, well, let's not get fancy yet. I'll do the fancy stuff later. Then we must remember to return ID, otherwise we won't see it on output. Shorten that up just a bit and source it. We submit it to the command prompt. Now we can display the definition just by typing the name. And of course, we can use it by passing protocol and subject. So let's say protocol is 001. That's numeric actually, but paste will coerce it to character. And the subject identifier, let's call this subject B3. Could not find subject. Oh, of course. Recall that with my up arrow. I meant to say subject ID, which is the name of our function, and they get pasted together. Now, the fancy thing we didn't try was we could have supplied a default argument for sep. And we'll say by default, let that be a dash. But now we have a more useful function. If we want to change our minds later about the separator, we don't have to rewrite our function. We just pass in an explicit value for the separator. Now, to make this work, we have to go inside our function body and say, don't automatically make sep a hyphen, make it whatever the user defined as sep. Now this gets a little confusing because here you say sep equals sep, and in any other language environment that would be self-evident, right? But here the left side and the right side have very different meanings. Here the word sep means the argument as identified in the definition of paste. Here the word sep means a variable that is stored locally, either because it was explicitly declared or because it was an argument, a formal argument in the function definition. So that's two very different uses of the word sep. And so it has substantive meaning in this context. So we could go ahead and redefine that, source it again, and now if we say subject ID, say A3, then we get our paste operation, but we could change our minds and say let sep be nothing at all. And the concatenation is slightly shorter. Of course, you should be aware that these are vectorized, so if you're working in a table context with a lot of subjects, it's easy to say something like letters, which is a vector, actually a predefined vector in R, and we could use the numbers 1 through 26 to correspond to those letters, just to have some material to paste together, and you see all the combinations. That's probably enough for exercise 1, and maybe a little more than you were asking for. Let's go on to number 2, and I'll just put that on screen real quick. Exercise number 2 says, write a function that normalizes weight by some typical value, rounding the result to 3 significant figures. A very common operation, really. Let's put that down here. You can still kind of see it out of the corner of our screen. Again, the process, first find an informative name for our function. Let's call it weight norm. How's that? It at least reminds me of what I was thinking. Hopefully it reminds the user as well. And what's it going to be a function of? Let's see, normalizes weight by some typical value. Well, obviously we need to force the user to supply weight. And let's see, by some typical value. Weights, probably weights are going to be in kilograms here. Typical value might be 70. Or, let's be really fancy. Let's make the typical value just be the mean of whatever the user supplied as weight. So we'll say tip for typical value. And we'll say mean weight. Watch out, that will bite you if there are NAs in the weights that you pass. Right now we're not going to pass any NAs, so we can get away with just saying mean weight. There will be no error in that case. And let's see, rounding the results to 3 significant figures. You know what? We'll write something that rounds to 3 significant figures, but we'll make it something the user can modify if they want. So we'll say sig equals 3. That way we can change our minds on the fly and not have to rewrite the function. Okay, so we have weight. We want to normalize it. So we'll say norms, that's normalized weights. Let's set that to weight divided by tip. Hopefully that won't be 0. We'll talk about error trapping some other time. Now we want to make sure that we don't have really ugly values like, 21/6 would be, well, not so bad. Lots of decimals like that. We don't need 4 or 5 decimals for weights. We probably only need 2 places. So let's quickly look up the help for significant figures. And it's defined somewhere in here. There it is. Significant figures. Takes an x, something we're trying to coerce to a certain number of significant digits, and you have to specify how many digits. That's what I was looking for. So here we'll say norms. Let's overwrite the variable itself. We'll say signif norms. And we'll say digits. Remember, that's the name of the argument as defined by signif. And then we'll say equals sig. And here, this is the name of the argument as we've described it. We could have used their convention, which would make things more like the sep equals sep construct we saw above. But this is correct, and if it's communicating to you, then it's sufficient. Now, the last thing we have to do, of course, is to remember to return this value. Otherwise, we don't get much interesting use out of our function. And now we have a complete function. We'll source that and invent some weights. Let's say weight normalized. Let's pick something like, let's normalize weights like all the weights from 55 through 67. And this is how they look. All numbers close to 1, which is what you'd expect. And the mean of those is being used as the typical value. You could have also said, let's make the typical value 70. Suppose that these are all adolescents or pediatrics, and we want to see their weights normalized by a typical adult value. And now we see all values less than 1, as expected. Question number 3 from exercises 3.4.1. Write a function that normalizes x by its median and rounds the result to n decimal places. Okay, very similar to what we've done right here, except now we are going to be normalizing by a median, not by a mean, and we're going to be rounding instead of doing signif, taking significant digits. So let's get the rhythm down here. We need an informative name for our function. Call it mednorm. How's that? And it's going to be a function of, well, x anyway, right? And normalizes by its median. You know what? The user doesn't need to supply anything regarding the median because that's part of the definition. We can just do that internally. Round the result to n decimal places. Well, whoever specified this didn't even say how many decimal places should be in play here, so we better make that a variable available to the user. But we could set a default for it. Let's say n is 2 decimal places by default. A little more utility there. So we've kept the spirit of the exercise here, because we are going to round to n decimal places, but it never hurts to be a little extra helpful. Let's say, let's define a y. Up above we did some overriding where we said norms equals some function of norms. Here we're going to use an alternate strategy, which some people find more appealing, where we invent something new instead of overriding the thing we were working on. That's sometimes smart if you might be using that same thing in other ways later in your function body. So we're going to make y some function of x. We'll use median. Y is median x. Again, if there were going to be NAs, you might want to trap them at that point. We're not going to worry about NAs for the time being. And then we're going to say, well, let's make it z just for illustration. Z equals round y. And here we need to put the n in. Again, we could guess, but it's safer to go to the help for round. Oh, you know what? It was right there. Anyway, round x digits. The same terminology applies here. We could say digits equals n. That captures the user's choice or the default choice if the user didn't specify. And, actually, if you look at the definition of round, it's really trivial, isn't it? It does not accept the ellipses, like trunc would. It only has two arguments. X is almost always going to be first, so you almost don't need to bother identifying the second argument by name. Okay, that's pretty clean and ready to go. We're going to source it. And we'll say mednorm and pass some interesting values for x. Well, great. R executed exactly what I asked, but it didn't do anything with it, at least not anything interesting, because I forgot to specify a return value. And you might be thinking, he did that just to teach a lesson, and the answer is no, it was an accident. That's much better. Well, I'll just recall the previous command here. Where'd it go? There it is. Okay, normalizes x by its median and rounds the result to n decimal places. Y equals median x. No, I've done this all wrong, haven't I? We should say tip equals median x, and y is x over tip. That's what we meant to say. If you look at it, you say to yourself, we could probably write this all as a one-liner, but I'll leave that as an exercise for the curious and just define that and try it one more time on the command line. That's the result we were hoping for. Now we see x, but x normalized actually by the median value this time, and not displaying much more decimals than we would find helpful, just rounding to the nearest, at least to the nearest two decimal places. That is all the exercises from 341. Hope that helps. You can ask another question about something if you'd like further detail, or we could go on and try something else. Let me know your interest. I thought this one was really interesting. Oh, wait, someone has a question? How about 361, exercise 361? Sure, be happy to take a look at those with you. And I'll put those on screen for a moment. You know, it would be nice to make this a little smaller, use my real estate a little better and get it all on one screen. Every time I resize the screen, I lose my console. I'm not sure why that happens. You've probably figured it out already. I'm gonna do that. Let me know if that's too cramped and we'll rearrange real estate, but that lets me see my exercises and the workspace at the same time. The first challenge is to write a function to evaluate the quadratic formula. Ignore unexpected arguments and return the additive root by default. So obviously there's two solutions to the quadratic formula and you can't return both. It's a law of R that every function returns only one value. So we're just going to pick one as default, but we're going to let the user specify the other one if they have that interest. We also need to ignore unexpected arguments. That just means we need to include ... in the argument list, the list of formal arguments. So we probably don't need this material very much. I'll leave it over here. It gives us a little more space to work. 361. Okay, so we could start with something like this. We could call our function quad. That's reasonably informative. And you see that the quadratic formula has, of course, A, B, and C. So we're going to define those and let the user specify them. We're also going to let the user specify which root they want, you know, the additive version or the subtractive version. And the ellipses let us tolerate and ignore all other arguments. So we'll do some open parentheses. And I'm cheating here. I'm doing a little copy and paste, but I'll walk through it a line at a time, so that makes more sense. Okay, this animal under the radical is called the discriminant. Yeah, I didn't memorize that. I had to look it up somewhere. And we're going to calculate that initially. And then, again, some of this could be written more succinctly, but it's helping me to think it all out here and explicitly take the square root of the discriminant because then that lets me put in the choices in ways that are going to be very obvious to whoever has to read this function later or maintain it. We're going to say, okay, the default for positive is true, the positive version by default. Excuse me. But we're going to say if not positive, then we're going to let root be its opposite. Now root might have been negative already, in which case it flips positive, so don't confuse the use of the term positive up here. That doesn't mean necessarily that the discriminant, that the root of the discriminant will be positive when it's all done. We're just trying to identify the different versions of the return value. Excuse me. Now this is interesting here. So some people would write it this way. Let me just comment this out for a second. Gives it a chance to explore some nuance here. Some people might write, if positive does not equal true, then let the root be its opposite. Now that's perfectly legal syntax. You could also do an if-else approach, but I'm not sure that we want to get into that right now. My argument, though, is that, look, we've already defined positive as true, and by default, that's already a logical variable. If you go down here in the command line and say, what is the class of the word true? We find out it's a logical. So that means we can use logical operators on it. And the exclamation point all by itself reverses the logic of a logical variable. So we could say, if not positive, that's the same as if positive does not equal true. I like that better. It's a little more direct, a little more compact, and I think just as informative. At that point, we've checked for root reversals, and now we can look back at our definition of the quadratic formula and see that we only need to apply the negative b and the divide by 2a. And we can do that using explicit grouping of those arguments with parenthetical syntax. And now we have a pretty good look at things, except we need a return value. Well, hey, I just realized that the return value by default is the last expression evaluated. So we could just leave this exactly as is and have the result we want. Sometimes it's nice to be a little more obvious for your readers and say something like return value is going to be this. That way if you change your mind later and want to dress up the return value, you still have a chance. But now we have to explicitly return the return value, and we'll go ahead and do it that way. We'll source that and try to find something as a test case, like maybe this. Oops, what happened to my return value? There we go. I'll just paste an example down here. Now you see that I said d equals 6. Well, when we run this thing, R is going to say, well, I've got A, B, C in positive. I don't know what D is. We'll just collect that into the ellipses and not worry about it. And indeed, the function does not do anything with something called D, but it does tolerate it. So we can go ahead and evaluate this. And we get an answer of a -1. Okay, section 361, question number 2. Write a function to calculate AUC in terms of dose clearance and bioavailability. Assume bioavailability to be 1 if not given, and there's an expression for dose in terms of AUC clearance and bioavailability. So what we need is a function declaration that deals with things like dose and clearance, and we'll use F to represent bioavailability. And here we've assumed it to be 1, as promised. So then all we need to do is set up some parentheses and calculate clearance as clearance over F. And we could do this in more steps or fewer, but for now we'll just return dose over clearance. And that's just by rearrangement of the equation given. That works pretty good for AUC. And let's see here. Let's take AUC where dose is, say, 50 and clearance is something like 8. Source that, and we get an answer for AUC. Okay, I see another question pending, so I'll move on and do exercise 3613 now. Suppose most of your data files are tab separated with headers and have dot to represent missing values. Write a wrapper function for read table that sets these arguments so that the caller only needs to supply a file name. Use ... to let the caller set other arguments. Is the caller able to override your value for header? Now, this is really a mouthful, or a pageful, if you think about it. There's a lot going on here. One thing we should do, for starters, is call up the help for read.table, because that's the function we are wrapping. And you see that read.table has bazillions of arguments. And there's no way we want to specify all of those. I mean, that's just too much work. But we could do a few. So we could do something like, well, what are we doing? My read. Okay, now this is my way of reading something. And this is going to be a function. And what are the things we care about? We care about what the missing values are. And you see in the help for read.table, there should be down here something that, here it is, NA strings. That's how we're coding missing values here. So my function is going to have NA strings in it. It also should probably have X. Sorry. And X is the file name in this case. You know what? We'll name it exactly the way table names it. We'll call it file. That's a convenience. File, NA strings. What else is of interest here? Our files are tab separated. Most of our files are tab separated with headers. Well, look at the default for read table. Headers equals false. Here we're going to say, no, ours are different. Header equals true. And note though that instead of hard coding that in the function body, we've just applied true as a default value in the argument list. And that means that our users are going to be able to override that if they want and say, nope, I like your function, but in this case I just happen to have one file with no header. So that's nice. NA strings, of course, we can supply a default for, because in most of our files the default is a dot. That's the common usage, say, for an NMTran data set on its way to a non-mem estimation run. So that is as specified in the problem. And I think we got most of it. Tab separated. That should be the default for a read table. Let's just verify that over here. Let's see. Tab separated. Sep equals space. Well, here it says it just has empty marks, but I believe if you come down here and look at the sep, if sep equals the empty space, then the separator is white space. That is one or more spaces, tabs, new lines, or carriage returns. There's your definition right now. We say, hey, we like that behavior. That's nice just the way it is. Again, we'll probably give the user the option to override that. So we'll put the ... dots in here like that. And then we will open up some curly braces. And this really is a one-liner. So the curly braces here are just to control the real estate on the screen here, because I want you to be able to see this all without making the page any wider. Now literally we are just going to call read.table. We're going to say file equals file, because we're using those terms in exactly the same way as read table. We'll say header equals header. We'll say NA strings equals NA strings. This is what wrappers do. They just pass everything on through the way it is. except for a few things that they really care about. And we'll say, hey, all the things we don't care about, we'll just pass them on through like that. That pretty much does it. We'll just go ahead and source that. But not having a file at our fingertips, we're not actually going to demonstrate that at the moment. In the solutions that I post in a few minutes, there will be some code to generate a file that you can test. That's 361 in a nutshell. There is another question about exercises 341, which we'll get back to right now. The question is, what is the difference between rounding the result of n significant figures and rounding the result to n decimal places? Are they the same? Wow. I gotta think about that for a second. What is the difference between rounding the result of n significant figures? So I think you mean do signif first and then round that. And is that the same as just rounding? I don't know. That's a good question. I think they're going to be pretty similar, but I'm a little worried about that last digit. Because if you do signif first, then there's already going to be some operations that are very sensitive in the last figure. And again, round also has its own rules for what to do with the last figure. I can promise you this, signif and round are not the same thing, right? Because if you get a big old number like this, and sorry if you already know this, you know, if we talk about signif, then we're talking, if we say signif where number of figures is 3, we're talking about these 3. But if we say round to 3 figures, then we're going to preserve all these 3. So I'm going to say, I don't know. You just have to experiment with that, and play with it, and see if you can get the result you expected. It's a very interesting question. I can't give a good answer without testing some scenarios. And one of you is answering, there is a difference. N significant counts the number of digits to count before stating 0. I'm not sure exactly what you meant there, but I'm going to put your answer on screen for those who are interested and break it up a bit. Someone says the following. N significant counts the number of digits to count before stating 0. Now, is that in the help somewhere? I think a good thing at this point would be to open up that help and read very clearly what these functions are doing. Fortunately, they are all in the same file, the same help file. Round and signif. Round rounds the value in its first argument to the specified number of decimal places, and signif rounds the values in its first argument to the specified number of significant digits. Right, and so if you use the two functions in combination, then you got a slightly different animal. And more feedback from the class. For example, when 4561 is written in 3 significant number, it is written as 4560. Yes, I agree with that. But there would be no decimals to deal with. Yeah, so if you just took this and take that to the third significant figure, we get the expected result. And if we just arbitrarily round that without saying anything else, as you point out, there is no difference because the default for the round function is 0, is no decimals. But you could round it more strongly than that. I think round accepts some negative values. What if you did this? Round to -3. And what that's doing is when the argument to round is negative, then it's chewing to the left of the decimal place. And it's essentially doing what signif normally does. But that's only true when you have values with nothing after the decimal place. I believe. If you had values further than that, I think you have to break out the cases into separate instances. Interesting questions. And probably there's a more precise answer, but you see the general trend of the logic there. We still have 8 minutes or so left in the class. I'm happy to stick around and answer anything else you want to talk about. I'm seeing a comment. Historically, a significant number is used when dealing with big numbers like Avogadro's number. And use of scientific notations with n-significant numbers. Yeah, round and signif are very different things, and you have to know precisely which of those you want to deal with. I agree with that. One interesting difference, I know that as we just illustrated, round accepts negative values. I don't think it makes any sense to have negative values for signif. Wow, I'm wrong. Apparently it does. I wonder what happens here. Same thing. I'm going to have to go back and think about what that means. The help says, for signif, recognized values of digits are 1 through 22. Complex numbers are rounded to retain the specified number of digits, etc. Each element of the vector is rounded individually. So we just discovered an undocumented behavior of signif, that it does accept negative digits and does that kind of round-like approach where it starts chewing the other direction, I guess. Or maybe just everything less than 1 is treated as 1. So you're getting us one significant digit. You said 1 You get that. If you said signif to 0 significant digits, you get that. That's what's going on. Okay, I see another question. Sorry for the distraction. Does listing 3.15 serve the same purpose as listing 3.9? Let's take a look. Listing 3.15. 3.15, is that the same purpose as listing 3.9? Let's look at 3.9. Okay, 3.9 computes a power pretty handily. And listing 3.15, no, 3.15 just multiplies y by 2. The whole 3.15 is a really useless function, actually. It accepts no arguments, and it actually does something dangerous. It looks for y in your global environment. You really should be passing y if you want to calculate something on it. So I would say no, they have different purposes. 3.15 is just for illustration of the scoping of variables. And one of you is supplying an illustration about the difference between round and signif. I'll just print it on screen for those interested. We could take round of that value, and I'll bet we're going to do signif of the same value. We are. And say, yes, absolutely. Round scoots us up to, let's see, round, yeah, it takes us to 2 decimal places, whereas signif takes us to 2 significant figures. It's really the mantissa, like rounding the mantissa in scientific notation. Maybe that's what you were trying to say earlier. Well, it looks like we've covered the bulk of the material and handled your questions as well. So we could probably call it a day right there. I will hang on for a couple more minutes if someone wants to stay behind and ask something else. Otherwise, thank you, and see you back here next Tuesday for Chapter 4. Watch on the course website. I'll be posting a complete set of solutions in just a few seconds. Thanks.